Hello, everyone. My name is Alyssa Harder with Rohde Schwarz. I am a channel sales manager with them and have been an oscilloscope specialist the last few years. Today, we are very pleased to present 5 tips and tricks oscilloscope measurements. Today, we'll be talking about the oscilloscope side, and my esteemed colleague, Jeff Kyle, on Thursday will be talking about the probing side. You can use the same registration link to register for both, and we'll send you a reminder if you'd like to join the second session coming up on Thursday. I also have with me Greg McCaskill, so he'll be helping me attend to this session. If you have any questions, there's a question tab in the GoToWebinar section. You'll be able to enter your questions there, and we can answer them for the group at the end of each segment. At the end, if there's anything else burning that we haven't covered, I'll do the best to answer it today. Or if not, and it requires a little bit more preparation, we can potentially show it on Thursday as well. This session will be recorded and will be available for sharing if you have any colleagues who would be interested after the fact. With that, we'll go ahead and get started. So today we'll talk about 5 tips and tricks on how to make the best oscilloscope measurements. All right, so we'll start with selecting bandwidth, moving through maximizing vertical resolution, the trade-offs between sample rate and memory depth, reducing noise, and maximizing update rate. So we'll start with selecting bandwidth. So tip number 1, how much bandwidth do we really need? We typically recommend 3x the bandwidth for trigger and decode applications and 5x the bandwidth for compliance. We do need to consider both the oscilloscope and the probe bandwidth. This is an important distinction that we'll look at on the scope. I've got a 4 gigahertz RTO in front of me right now, but most of today's demonstrations will be using just simple passive probes that come with the oscilloscope. These passive probes typically have a system bandwidth of only about 500 megahertz. So when we put our 500 megahertz passive probe on the front end of a 4 gigahertz oscilloscope, we're effectively getting only 500 megahertz out of our scope. There are a couple tips that you can do. You can cable in to get the full bandwidth, but then you're typically limited to 50 ohms. The major trade-off there is the voltage. Typically in a 50 ohm mode on most oscilloscopes, you're limited to about 5 volts. It's usually written on the front panel of the scope. So we'll take a look at defining bandwidth. So we had said 3x to 5x, but what does that really mean? We define bandwidth as the crucial parameter for an oscilloscope. So this is where the amplitude or the attenuation is down 29%. So if you're using the oscilloscope at the rated frequency, you're already going to have some amplitude uncertainty. We define it using a sine wave. So this is an important distinction. So on the left-hand side, we see full amplitude. On the right-hand side, we see at the 3 dB down point that we showed in the previous slide, and we see some amplitude degradation already. This is all well and good, but we don't typically measure sine waves. I think most people on this call probably are measuring some sort of a square wave or a digital communication signal. So how much bandwidth do we really need to test these real-world signals? Back in the day, we probably all took a Fourier theory math class where we had to add up a series, so our fundamental frequency is shown on the top here in that purple or dark blue. So that's our fundamental. As we start adding the odd harmonics, the 3rd and the 5th, these are 3x and 5x, that original fundamental. As we add these, we start building it up, and it looks more and more like a square wave here with the teal signal here. So we typically need 3x or 5x. 3x meaning we're including that 3rd harmonic, 5x meaning we're including the 5th harmonic. In most cases, at the low frequency, like I2C, CAN bus, it's not a real cost difference going between the third harmonic and the fifth harmonic. You can typically use the same oscilloscope to do that. When we start getting up into DDR, you start changing the oscilloscope requirements, going from the third to the fifth harmonic. So it's important to understand if you're only doing basic trigger and decode, debugging, not trying to test any compliance applications, you could probably get away with just the third harmonic, and this can save you tens of thousands of dollars. So it's something to consider. We do aspire for you to reach that fifth harmonic if you're able to, but the third harmonic will give you reliable results. So something else to consider is the fastest system edge. So this makes sure that you have enough of that high frequency content so that you get a really sharp rising edge. If we go back a couple slides, we remember that the square waves are made up of a number of harmonics, and the more harmonics you add, the sharper that rising edge. It is possible, this is a little tough sometimes to wrap your head around, but it is possible to have low speed signals with a high speed edge. So a signal that comes to mind that most of us have used is a probe compensation signal. This might have only a frequency of 10 kilohertz, but it has a lot of high frequency content to get that really sharp square wave look to it. This is all something that is specified in the data sheet. I know most of us don't go looking to our oscilloscope data sheets to find out our rise and fall time, but it's always there, and it's specific to a particular oscilloscope or manufacturer. So in this case, we have listed 0.43 divided by the analog bandwidth. So this will change oscilloscope to oscilloscope, but it is something you also need to consider. So we'll jump over to the oscilloscope real quick here. We'll do a preset. So in each section, we'll jump back and forth between the oscilloscope and some slides. We'll have a live demo.
Hi, everybody. Greg McCaskill here. I just wanted to remind you, you can type in questions in the question section or the chat section, and we'll be monitoring that and answering those as we go along. And I've got one for you in a second, Alyssa.
Okay, we'll go ahead and do this demonstration real quick, and then we'll jump back over. So right here, I have a fairly simple 10 megahertz clock. I've got a small demo board in front of me. So what we're going to do is we're going to take a look at what happens when we limit the bandwidth. So 10 megahertz is a nice round number. So if we limit our bandwidth down to, say, 5 megahertz, let's see what happens to our signal. So at 5 megahertz, we don't see a square wave anymore. We see a sine wave. So we can save this as a reference so we can compare. Now let's go to 10 megahertz. So this is 1-to-1 bandwidth to the signal of interest. Nope, I lost my trying to probe here as well. All right, so we've got our 5 megahertz, the one with the reduced amplitude. 10 megahertz starts to look like the right amplitude, or at least close to it. And now if we go to 3x, we'll see how that changes. So 3x, we start to see more of that square wave. We'll save that as our reference as well. And now if we go to 5x, which is what we typically recommend for compliance, we start seeing an even sharper edge here. We'll save that one as well. And then go to completely over bandwidth. And we see a nice looking picture there. So I'm going to stop this so I don't have to hold my probe. And we can zoom in on this edge here. So we see that as the bandwidth increases, we get a much sharper rising edge. So down here, that really flat looking line, that was at 5 megahertz. So we were at half the bandwidth. That's not considered a good measurement. The next one up that looks a little bit better is our 10 megahertz. So that's 1-to-1. And we're still seeing that sine wave looking signal. And as we start to move to 3x, 5x, and 10x, our frequency of interest, we start seeing what we would expect, more of a traditional square wave. Okay, Greg, questions?
Yeah, we had a question. It says, do I have to use an active probe to get full bandwidth of my oscilloscope?
No. So we do recommend active probes in general. You will get the fastest rising edge by doing that. If there's a lot of questions about probing, I think you're really going to be interested in Jeff's discussion on Thursday. One of the other things that you can do is cable directly in or solder into your device. The only difference here is that a 1 mega ohm connection that a probe typically has is perhaps 200 volts peak versus in the 50 ohm cabled connection, you're at 5 volts. So one of the more common ways that people can damage the front ends of oscilloscopes is by leaving a scope in 50 ohms and putting a higher voltage signal in. Even something like a 12-volt battery could damage the front end. So it's something to be careful about, but cabling in, if you've got good cables, that's the easiest way to get the full bandwidth out of your scope.
Okay, perfect. That's the only question at the moment.
All right. So we'll jump back over to the slides. We'll go back through our second tip here. We're going into vertical resolution. So tip number 2 is maximize vertical resolution. So use the highest resolution oscilloscope available. Show about 80% of the signal on screen for best resolution. We recommend about 80% because there are times where we'll see people have the signal that's clipping. It'll be off the screen. That's not a great, reliable way to take a measurement. Another common thing that happens is people want to be able to see all 4 channels on the oscilloscope screen. So what happens is everyone cranks down the vertical scale, so each of the 4 signals sits neatly in about 25% of the screen. It's a convenient way to view the oscilloscope signals, but you're giving up resolution when you're doing that. So we do recommend about 80%. When we go to the oscilloscope, I can show you some tips on ways you can set up the display so you're not giving up that resolution. So when we talk about vertical resolution, we can talk about what an oscilloscope fundamentally does. And in an ideal world, we'd have a continuous measurement of infinitely small voltage deviations across infinitely small time deviations. So we would have no gaps in time, and we would have infinitely precise vertical steps. In the real world, we really are plotting and measuring these discrete voltages, and we can't do that continuously. So we have to do it at a particular rate. So that's our sample rate on the horizontal scale. And on the vertical scale, we have to either round up or round down. That's what we call a quantized level, but you could think of them as stair steps. So there's only so many stair steps available on the screen. So we want them to be as small as possible so we can determine more precise voltage levels. So I like to think about it in terms of the camera. So we can think of the vertical resolution similarly to vertical megapixels. So with an 8-bit oscilloscope, you would get good resolution. You can see that it's a flower on the left-hand side, but if you tried to zoom in, you wouldn't really get any additional signal detail. On the right-hand side with 10-bit resolution, we're seeing a little bit crisper, a little bit more. If we zoom in, we could see those petals more distinctly. We could see, the stem from the leaf. These are types of things that you can do on an oscilloscope too, so we'll take a look at what that looks like. So on a traditional scope, you have 2 to the power of your ADC, and that's how many steps are on your display. So on an 8-bit scope, it's 2 to the 8th, or 256 levels. When we go to 10 bits, we get 4 times the additional levels, so 2 to the 2, or 4x. So we can see that on the left-hand side, that level or that swing from the bottom to the top is quite large. When we go to 10 bits, it's much smaller. So what does this actually look like on the scope? So our oscilloscopes on the RTE, the RTO, and the RTP have the ability to go up to even 16-bit resolution. So on the left-hand side, we can see that there's a small sine wave, perhaps riding on top of a larger sine wave. The lower part of the screen, we're zoomed in on the top or the crest of that sine wave. On the right-hand side, we can see it much more crisp. We can see those individual changes. So this is kind of like really zooming in on a hardware zoom versus a software zoom in a camera. All right, so that was a quick one. We'll head back to the oscilloscope. And again, you can get your questions into Greg. All right.
You had one come in about this. It says, are more bits always better, or is there a trade-off?
So in general, more bits will be better, but it's not dependent on only the bits. So there is a noise component of this as well. So we'll take a look at that actually a little bit later on as well. We'll get my signal up on the screen here. All right, so we've got a relatively low speed signal here. It's an I²C signal, and on my board there's some crosstalk between the clock and the data. So on the left-hand side, about 3 divisions in, we can see that there's perhaps some sort of a blip or some crosstalk coming in from when the data signal goes low. What we can do, so we can actually use HD mode. This is how we get up to 16 bits. And we can trade off bandwidth for bits. So if we start at 2 gigahertz, 10-bit resolution, we start stepping down. We start seeing that as we add more resolution, reduce that bandwidth, that we see that very, very clearly. So something that we can do as well is on most oscilloscopes, you're limited to the trigger sensitivity in an analog trigger system. We have the ability to change how sensitive our trigger system is. So if you have a very noisy signal, you perhaps want the trigger system to be very insensitive. In this case, we want it to be very sensitive so we can just trigger on when that blip happens. So we'll go noise reject and make this only a few pixels on the screen. So as we bring this trigger level up to that blip, we'll see it move over to that triangle now in the center of the screen. So I'm moving our zoom window. And now we're stably triggering on that little deviation on top of a 3-volt signal. So we're stably triggering on something that's very, very small on top of that 3-volt. So that's something that you can do because we have that added resolution to be able to pull that out of the noise. So you can not only see the smaller signals, but also trigger on them. All right, so we'll go back to the slides here. So maximizing, oh, There we go. Maximizing sample rate and memory depth. So out of the topics we've covered so far, I think this one is the least understood. We're on to tip number 3, maximize sample rate. So we need to be careful of sample rate and memory depth trade-offs and use the deepest memory oscilloscope available. An alternative to having a really deep memory oscilloscope is using infinite persistence to build up a worst case scenario. This happens if you can only capture small time periods and you need to capture longer time periods and get a view of how something might be changing over a long period of time. One of the most common things I've seen in the last couple of years is people confusing not enough bandwidth and seeing the effects of not enough memory with not enough bandwidth. And so they might see something that looks like scalloped edges, and we'll take a look at what that looks like on the actual scope. But a lot of times when people see something like that, they think, I need more bandwidth, and a lot of times they just need more memory. Memory is probably the single most improved data sheet stack in the last couple of years. So obviously everyone's racing to higher and higher bandwidth, but in the under a gigahertz space or even under the 10 gigahertz space, there's a lot of oscilloscopes now where it used to be standard to have only 1 or 2 million points, and now you're perhaps getting 80 or 100 million for approximately the same price. So this is something where the newer oscilloscopes in the last 2 to 3 years have made great strides. We'll take a look at why that's important. So if we look back at our discrete timing measurements, so we're taking a discrete voltage at a discrete time. We talked about we want those vertical steps to be as small as possible. We also want our time steps to be as small as possible too. So our sample rate is how often we're taking these measurements. So we want the sample rate to be nice and high and maximize that, and we'll talk about the trade-offs that present themselves. So on an oscilloscope, we can think about our sample rate as a horizontal megapixels. So if we're not taking measurements at a frequent enough interval, we'll completely miss a blip that happens here. So it's often confusing when we see these perfectly connected lines on an oscilloscope, but on this previous slide, we see discrete data points. So what happens is an oscilloscope might take a measurement here and take a measurement here and interpolate or connect the dots in between. So if you don't have enough sample points to indicate that there is an interesting transition, like here, the oscilloscope will just simply connect the dots from the lower end to the higher end. And there's more behind it than that. There's sin x over x interpolation or other types of algorithms. But what the oscilloscope is actually measuring is a discrete data point. So on most oscilloscopes, you can go in and actually show the data points versus the interpolation. So we can take a look at that on the oscilloscope when we switch back over. But it's important to remember that the scope is measuring discrete data points. So some of us may be familiar with the Nyquist theorem. So this requires that the sample rate be at least 2x to recreate the signal. If you're doing something basic, like on the left-hand side here, like a slow serial bus, 2x is plenty. You don't really need to know a lot of the different transitions. You're really looking for, can the oscilloscope make out a 1 or a 0? If you're trying to do more on the signal integrity side, where you're trying to characterize individual transitions, you really need more data points to recreate those signals. So this is possibly my favorite slide in this whole presentation. So at the bottom, we're looking at what the oscilloscope actually sees at a sample rate that's too slow. So if we look at 1.25x, we can't even really see that it's a sine wave. We completely miss some of those high transitions. We only get some data points at the low end. we go to 2.5x, which is technically compliant for Nyquist, we can see that there's transitions at the proper frequencies. But to me, it doesn't really look like a signal. It looks very sharp with not a lot of signal detail. As we go to 5x, it starts to look more like a sine wave. And at 20x, I feel really good looking at that, comparing to the actual signal, that this is a good recreation. It's something that it's hard to picture what the scope is doing unless you change it into dots mode or turn off that interpolation. So we'll move back over to the scope and show what happens when you don't have enough sample rate at the very end here. But in the meantime, if we've heard sample rate is so important, why would we ever use less than the maximum sample rate? So why would we ever use 2.5x or 5x versus 20x? And the short answer here is that memory depth is limited. So it's not that we can have this infinite resource of memory. We take the fixed memory depth that's available in our oscilloscope, we divide it by the sample rate, and that's the amount of captured time we can get. But the challenge here is that the memory depth is typically fixed, and the amount of time that we're trying to capture is also typically fixed. So if those two are fixed, the only variable here that we can change is the sample rate, and typically it goes down. So here we've got a couple different classes of oscilloscope, how much memory is typically available on that class, and then what's the maximum amount of time at a relatively quick sample rate and a relatively slow sample rate. So we can see that in a handheld oscilloscope, you're really giving up the memory depth that you might get on a basic or lab scope. A really common challenge that we see is in the automotive space. We'll see engineers, a lot of times mechanical engineers will say, look at this signal for 5, 10, 30 seconds. Because that seems reasonable when you're looking with your own eyeballs at something that's moving and physical. When we move over to the electrical space, it becomes very, very challenging to look at something for seconds. We're typically used to dealing with nanoseconds, milliseconds. So when we go to full seconds, that's a lot of data that we're having to capture. So in some of those cases, they've actually had to invest in a higher deep memory oscilloscope to make some of those long measurements, even though it's relatively low speed signal. So it's something to consider. Again, this is one of the biggest leaps that oscilloscopes have made in the last couple of years. A basic bench scope, maybe in 2010 or 2015, might have only had a couple of million samples. Now we're up to 20 million. So it's, time marches on and the technology gets better and less expensive, and we see it trickle down from the high end, being able to implement that in a more affordable basic bench scope. All right, so we'll switch back over to our oscilloscope here.
Alyssa, we did have one question related to sample rate. Is the scope always running at maximum memory depth?
The scope is not always running at max memory depth. So it's something that you can control. The reason that you might want to limit the memory depth is if you don't need these long time captures, you can reduce your sample size to something more manageable if you're trying to do remote data transfer or save something off very quickly to a USB drive. Having this really deep memory is great, but when you start getting gigabit files coming off, sometimes it's more manageable to have something smaller. All right, so we've got our sine wave here. Change to 50 ohm coupling because I'm cabled into an 825 megahertz source here. So what we're going to do is I'm going to put a frequency measurement up, and we're going to see what happens as we change our frequency or change our sample rate. So right now we're measuring, it's hopping around a little bit, but in the 825, 830 megahertz range. So one of the things we can do to force the sample rate lower is to start capturing more time. So right now at the bottom of the screen, you can see the time per division is annotated. We're at 10 nanoseconds. So as we start capturing more and more time, we'll see that the sample rate in our top right-hand corner of the screen, which currently reads 10 gigasamples per second, will start to drop. So we would expect that for an 825 megahertz signal at 2 to 3x, we'll start seeing an effect a little bit below 2 gigasamples per second. So I'm turning my horizontal scale, increasing the time per division. So we're at 400 nanoseconds per div, 500 microsecond. We'll keep cranking this out. And so now we're down to 5 gigasamples per second. And now as we go to 2.5 gigasamples per second, and all I'm doing is continuing to add more and more captured time, we start seeing our 825 is still correct. As we drop down to 2 gigasamples, we're still correct. And at 1 gigasample per second, we see our frequency measurement is now incorrect. So it's aliasing. So as we go down to 500 megasamples per second, we start to see some of those scalloped edges. As we go down even further, we see more of that scallop effect happening. And a lot of times when people see those edges, what appear to be rounded off, kind of like what we had in that first bandwidth discussion, it's really that there's not enough memory to create those sample points. And so it becomes bandwidth along with that sample rate. But it's not really that the oscilloscope doesn't have enough bandwidth, it's that the sample points aren't frequent enough to recreate those high-speed rising edges. All right, so we'll get out of aliasing because quite honestly, it makes me a little nervous looking at that screen because I know it's wrong. And we'll go back into our sine waves here. So what we can do, we'll get rid of that frequency measurement. And if we go to display, something that we can do is get rid of our vectors and show just dots. And so if we do a run single, we keep zooming in, we can actually, I'll turn up my intensity so you can hopefully see it a little bit brighter there on the screen. But you can see all those individual dots. And so the sample rate is how frequently those dots are being measured. So that's really what the oscilloscope is measuring. We see a nice, beautiful curve, but as we zoom in even more, we can see that those dots are at a steady distance apart, and we can start seeing those quantized levels that are shown. So something that we can change is the interpolation. So right now we have nothing set up, but if we change to sample and hold, we started seeing that we have those quantized levels. So for me, this helps bring it together of what the oscilloscope is actually measuring in terms of my vertical resolution, my horizontal resolution. We want to be able to plot those sample points anywhere in voltage and in time, but that's not entirely possible. So the better resolution we can have vertically and the better resolution we can have horizontally, we'll get a better recreation of the actual signal. All right, so if there's no other questions, we'll go back to presentation for tip number 4. So this is reducing noise. So tip number 4 is consider all sources of noise. So you can go down the rabbit hole of this pretty quickly, but a good place to start is the oscilloscope, the probe, the probing geometry. All of these things affect the measurement noise. A good tip is to use a low attenuation, low noise probe with short ground leads. So oscilloscope noise is additive to your signal noise. So even if you have a perfect signal like on the bottom, on the top, any noise that your oscilloscope has will be added and included in your measured values. So these are included in your peak-to-peak values, included in your noise measurements of your signal. So it's best to have an oscilloscope with low noise to begin with. Your noise floor depends on your sensitivity. So this is included in the slides. It's something you can do at home on any oscilloscope that you might have. It requires no probes, nothing hooked up, so you disconnect all inputs to the scope, and you select it to a small volts per division. So in this case, 1 millivolt per division, perhaps 2 or 3, or whatever the minimum is on your oscilloscope. And then you can go in and measure the ACRMS noise. It's kind of a easy, fun exercise to compare what you measure to the data sheet. We're all, a lot of us are still sheltered at home, so it's a good time to run your own lab experiment. But one thing that happens occasionally is some scopes at very low sensitivities will start doing a software zoom, so you don't actually get any better noise performance by going to smaller volts per div. So it's something to be aware of. Noise floor also depends on bandwidth. So on the top here, we have a time domain. On the bottom, we have the frequency domain that we're displaying in a log scale. So our noise is integrated over the full range. So in this case, from DC to, looks like we've got a 2 gigahertz cutoff. So if we change our cutoff to 100 megahertz, we see that measured noise go down. So we go from 151 microvolts down to 34 microvolts because we're cutting off that higher frequency noise content. So we're integrating only from DC to 100 megahertz in the frequency domain. So as we drop even further to 50 megahertz cutoff, we're integrating over even less noise, and so we see that drop from 34 down to 21. Probes also contribute to the overall noise. Everything that's spec'd in a probe data sheet is the best case scenario. You can always make it worse from there by having complex probe geometries or probing incorrectly in some way. So we start with, again, our signal plus our device plus our probing and probe noise, and then we ultimately see the combination of all that on our oscilloscope. Probe attenuation is something to be careful of. Whenever you're measuring noise and you're using a 10-to-1 probe, like a regular passive probe, you're multiplying your signal and the scope noise by this factor. It limits the max sensitivity setting, and it's just something to be very aware of. In certain applications where you are measuring noise specifically, like for a power rail, you might want to consider a dedicated power rail probe that has 1-to-1 attenuation. There's a lot of probes specifically designed for a particular job, whether it's high voltage where it has a very high attenuation factor, or something like a power rail probe where it has a very low attenuation factor. Something to be considerate of. So this last piece is a public service announcement for using short ground leads if you're going to use a passive probe. So I think most of us are familiar with the picture on the left. We've got that witch's hat with our long alligator clip ground lead. We pull that center section back, get a little hook, and it makes for very easy probing. Most of us have forgotten or lost the little package that comes with our oscilloscope probes, but there's many replacement parts out there. But you can actually pull off that witch's cap, that black center section. And when you pull that off, there's actually just that center pin, and you can take the little spring short ground lead and flip it over. So we still have our center pin, and off to the left there is our short ground lead. So we want to have a smaller area that signals can pass through, otherwise it becomes an unintentional antenna. So if we go to this next slide, Anything that's very, very small will have less additive noise. When we have these bigger loops, we start looking like a near-field probe. So these are not desirable. They're very convenient, which is why we all still use them and have them nearby. But it's just something to be aware of, that if you're able to use that short ground lead, it's a very low-cost way to greatly improve your measurements, even using a passive probe. One other quick tip here is, as we show our active probe, even on an active probe, you can degrade that performance pretty quickly by using all the fancy adapters that are in the accessory kit. So this isn't just for passive probes, something we consider it for all probes. All right, so Greg, I'll let you handle the questions and I'll jump back over to the scope real quick.
Yeah, thanks for checking in. First of all, I like how you called that a public service announcement. That was fun. That's my comment. But we did have one question, a statement and a question. You never mentioned solder in probes. Wouldn't that be the most accurate?
I think that's a great lead-in for Jeff's talk on Thursday. So Jeff will talk all about the different probing possibilities. So the way we physically connect a probe to our device. So we'll have that whole separate section on probing. So I invite you to join us then. Okay, so we've got a 10 megahertz clock here, so nothing all that exciting. So we can see here as we can add like a peak to peak or any number of different measurements here. Past it, there we go, peak to peak. We'll add that, so we're getting around 4 volts. So we're using the long ground lead, the one with the alligator clip and the witch's hat. So we can save this as a reference. And we see a little bit of ringing, a little bit of overshoot. What I would expect is a very perfect square wave. So now I'm going to switch my probe 6 here, and I'm going to go over to our short ground lead. So I'm literally pulling off the tip of the probe and carefully putting the short ground lead on. And now I just connect it. And it looks substantially different. So the hard part is I have to actually hold this probe here. It's a little bit easier to clip something on and be able to walk away. But we do get a substantially different measurement here. So instead of reading close to 4 volts, we're reading the 3.3 volts that we would expect for a TTL type signal. So I'm going to pause this so I don't have to continue to hold it. But as we zoom in here on the edge, we see that all the effects of that ringing were from our long ground lead. So this is pretty crazy that such a short ground lead can have such a large effect. So this is something that we recommend. If you lost the little probe pouch, there's many places like Test Equity or our spare parts department that would have these extra short ground lead tips. We highly recommend it if you're trying to make some of these rise time measurements or something that would affect that rising edge. Let's see. So we got a question in the chat. It looked like we had some questions about, do we have the part number for the short ground lead? I'm sure we do, but that's unfortunately something I don't know off the top of my head, so I can follow up with an email.
Yeah, absolutely. I'll note that, and it is specific to that specific probe. So we just want to know which model you're working with, and we could get you that. No problem.
Okay. All right, so we're in the home stretch here with our last tip. So that's maximizing update rate. So tip number 5 is maximize update rate. Higher update rate increases their test coverage and decreases test time. So, okay, we want more of it, but what is update rate? So this whole time we've been talking about how we perfectly recreate our signal in the oscilloscope. So we have our sample rate, our memory depth, our vertical resolution. So if we go back to that camera analogy, if we assume that everything is perfect, we get a nice perfect still shot that we can blow up, we can zoom in on. But update rate is more of sport mode, or how many frames per second. So that's how many perfect images can I take very quickly. So rather than taking something on a tripod and just taking one beautiful crisp image, we're trying to see, can we get 4K video instead of one image, 4K video versus a Polaroid. And that's definitely possible. So what we're typically used to seeing is something like on the left-hand side, where we see the trace is lively and it looks like we're capturing all this data. On the right-hand side, at first glance, it looks pretty ugly. There's a lot of stuff coming in and out there. We've got some runt pulses, we've got some timing issues, we've got all sorts of glitches going on. What's crazy though is that most of the time people are using an oscilloscope with a very slow update rate, like on the left-hand side. And it looks good enough and you don't know that there's a problem. So you don't know to go use a special trigger, something to go a little bit deeper and debug. So we can take a look at this on the scope, but what happens is that because we're only taking full captures every once in a while, these glitches can sneak in between captures of the oscilloscope. So during the time that an oscilloscope is processing the data and getting it to the display, you might miss all this other stuff that's going on. So one of the big things we can do is, once you see it, just during normal operation, you can go and dig in to the deeper details happening. So this makes a digital scope feel a little bit more like an analog scope where you saw everything. Digital scopes for the longest time had been very, very slow to update. So they're great for post-processing, getting data off, but very difficult to get that lively feel. So it's something that we have very few slides on this one, but we can jump back over to the scope because I think that's much more fun. So the main premise here is that we're looking at sport mode or 4K video versus that kind of quick glance and then look away. So theoretically, we'd be able to look at a signal for a smaller amount of time, but have better confidence in how it looks. Let's see. Getting hooked up to a new signal over here. I don't think I have my probe hooked back up quite right.
Alyssa, you partially answered this question, but I'll go ahead and state it so we can address it. So I never had issues with update rate on analog scopes. Why would I want a high update rate on a digital scope versus an analog scope?
Oh, that's a good question. I know there's still a lot of analog scope lovers out there. So analog scopes are still great if you can find them. Most people aren't making new analog scopes, so that's the first challenge. The second challenge is that analog scopes are typically limited to a couple hundred megahertz, and we're able to do this high update rate all the way up to 16 gigahertz now. So it's really a cool way to look at high-speed signals with this high update rate as signals are changing quickly. So one of the common assumptions that people make when they're trying to debug a signal. If they're looking for a very rare event, something that's happening only a couple times per second, what we often see is people saying, oh, I'll get my fastest oscilloscope, my highest bandwidth, fastest oscilloscope in the lab. And the logic there is understandable that, it's usually the most expensive oscilloscope in the lab, but a lot of times those scopes were designed for a very particular job. So they're trying to take that perfect single snapshot of an eye diagram. They're not trying to see all these dynamic changes. So a lot of times, something like an RTO or an RTP can be used to get those high-speed digital signals as well and get those nice recreations, but you also see the live changes. So if you were to touch a trace, or if you were to move a cable or rotate your device, you're able to see those changes real time. It becomes a little bit different way to think of how fast is my oscilloscope, how reactive is my oscilloscope. So a little bit long-winded there, but we do view analog scopes as very reactive, and now I think the digital scopes have caught up and they're able to have that same sort of response, but also allow you to post-process the data and save it off and save and recall settings and all the good things that we love about digital scopes. Okay, so if we go to our device here, so we can see every once in a while we have a trace that's too small. It's a runt pulse. So I've got the display showing a heat map. So anything that's brighter is happening much more frequently. So we can see that the pulse underneath is a little bit darker, so it's not happening all that often, but we do see that it is happening. So most oscilloscopes that don't have an optimization for update rate typically would look something like this. Oh, trigger hold off, sorry. And so we'll turn on a trigger hold off, effectively slowing down our oscilloscope. So every once in a while, we'll still see it pop through, but we still see the trace at the bottom looking very lively. We wouldn't immediately assume that there's a problem. So we can turn that hold off and go back to running at full speed. And we can see those runt pulses are happening quite often. So at this point, we could go in and use a fancier trigger to isolate that. So we could do a runt. So this will give us 2 trigger thresholds. So it has to cross the first threshold, but not the second. So now when we are looking at that pulse, we can see him coming in. One of the other things that's really important is on RTO, RTP, and RTE oscilloscopes, we can also use a mask, which still allows the scope to run around 600,000 waveforms per second. So we're able to use this as a way to capture when an event happens, or if we go into the mask, we can have it just run and get some basic quality analysis on the right-hand side here. So we can see how often it happens and go from there. So one of the other cool things as we look at this signal again is that we see these lively traces of up to 1 million waveforms per second without putting the scope in a special mode. So we're able to see this without turning on something special. So this is always your default view. And if you saw something like this, you'd be able to go through and take the steps to debug and figure out the root cause. But having that initial knowledge that, hey, something might not be quite right is what update rate really gets you. Let's see, it looks like we have a question about, is this the same as letting a scope run for a long time? And you can get the short answer to that is yes, you can get around not having high update rate by letting a scope run over lunch or over a weekend. It's a lot easier to just have it up front, right in front of you. So that's what we talk about at the first part of this section of test coverage. So you're able to have a higher statistical probability of finding these glitches in a much shorter amount of time. Okay. All right, so that concludes our tips and tricks. So the slides are included within this GoToWebinar as a handout. So they're already available and ready for you to download. A lot of the instruments that we talked about today our oscilloscopes are included in our latest promotion. They're fully unlocked, including all the serial trigger and decode options. Including the MSO and a lot of the other analysis options. Sorry, it sounded like I had an echo there for a second. But so more information is available at the Ask an Engineer site. Otherwise, the promotional pricing is available here as well. Most of these instruments are in stock through TestEquity, who has helped us to sponsor this presentation. And with that, we will open it up for a few questions. So I'll ask Greg to help me with the chat here.
Yeah, we had, hi again. We had one more of a statement. It says, glad to see the probe interface is BNC and not proprietary. So yeah.
Yeah, I can comment on that real quick.
Please.
So we do have probes available that are just regular BNC as well as a proprietary interface. So the active probes typically need power in some way to activate the amplifier. So for those, we do have a proprietary interface. For the passive probes, they can typically be used interchangeably with other scope manufacturers. For a lot of our current probes, we do have an option to have external power or powered by the front end of the scope. So there are some options there.
All right, perfect. And if you have questions, type them in. The last one that I have here from somebody says, you had what looked like an FFT showing at the beginning. Can you explain what was going on and what kind of math functions are available?
We'll go back to the scope real quick here. And let's see, I can put what we had up at the beginning again. Okay, so we'll change over to 50 ohms, and we've got a 825 megahertz signal up. We can add an FFT or take a look in the frequency domain. So we can drive this just like a spectrum analyzer, 825 megahertz. Our span, I know to be around 50 megahertz, and we can just simply apply it. So right now on the top, the blue trace is the time domain, so that's voltage versus time, everything we've been talking about so far today. On the bottom, we've got power versus frequency. So this is what you would typically look at on a spectrum analyzer, but we can do a Fourier transform on the scope, get a very, very fast FFT. So a lot of times people are hesitant to use these on a scope because they're too slow. This is incredibly fast. It's a very interesting, cool way to look at multiple FFTs at once, so multi-channel frequency domain analysis. So an oscilloscope has 4 channels. You can use all 4 channels as a spectrum analyzer input. They're really good at low frequency spectrum analyzer work, starting down close to DC. And then, Greg, I think you said the second part of that question was math functions.
Yes, what kind of math functions are available? Yeah, I guess those are, okay, it was all one sentence, but I think those are two different topics, yeah.
Sure. So for our basic math functions, most of these are available on our entry-level oscilloscope 2 that start around $1,000. But you know, plus, minus, multiplying, giving basic power measurements. You can do integrals and differentials. The advanced tab, you can actually get a full equation editor. So you can do things like looking at FIR filters, even doing a user-defined loading in through MATLAB. So there's a lot of cool things you can do here, as long as you can use a channel, a reference, a measurement as a variable.
Very good.
All right. With that, we'll close out this webinar. The recording will be made available to you, and we really appreciate you coming and joining Rohde Schwarz and Test Equity today. Thank you so much for joining us. Have a good rest of your day.
Thank you, everybody. Have a good day.